Well, we have a small group. I figured we'd do a quick round of introductions and keep this all kind of informal today.
Sounds good to me.
Mark, since I have you first, where are you from?
Yeah, my name is Marc Deschmane. I'm from Germany. I work in a science center. I'm part of the observatory team. Our day-to-day work is like observation of the sun mostly, because we are only open until 5 p.m. in the afternoon and rarely have evening sessions where people can see other objects of the sky. And we are currently debating about having our own remote telescope, so that we can actually ensure that our guests have more access to nighttime observation. And that's why I'm here, to learn about how you guys do it.
Excellent. We have, as you'll see, we have our own remote telescopes that we have built and put on the system. But over the years, many people have come to us with remote telescopes they put together. And we have just as many of those using our scheduling interface. Maybe that's something that will interest you.
Sounds good.
Let me turn to Anna. Yeah, we've had some technical difficulties here. So we can volume up that as well.
We can do a little bit.
Okay, while she's working on that, let me just check with the people in the room. Would you care to introduce yourself again for the benefit of the others? Okay, thanks.
My name is I live in Belgium.
All right, well, we'll be doing some observing today and some analysis. Okay, cool. And Anna, I don't know if you're there, if you want to introduce yourself, but you're welcome to now, if you care to. If not, we'll jump right in. So this is the third workshop, my Skynet. So if you listen to Michael Fitzgerald's talk, he talked about the Skynet Robotic Telescope Network, among many others. So this is Skynet. We're giving 5 workshops during this conference. This is the third, and they're all scheduled kind of out of order, but this would be the natural first one to attend. We've been building robotic telescopes since 2004. Initially, our core telescopes are called prompt telescopes. We were building them in Cerro Tololo, Inter-American Observatory, and eventually spread out into the form of a global network. Beginning in 2008, the network, as you'll see, was originally built for research, originally gamma ray burst follow-up, but now we do pretty much any kind of small telescope research. But in 2008, we started developing curricula for students to also use the telescopes, rebuilding our observing interfaces so that they can be used simultaneously by professionals and students, which is challenging, sometimes all the way down to the middle school level, though my focus is undergraduate. And it's turned out quite well. We have beginning in 2008, we developed our first curriculum, deployed it in 2009. It's called Our Place in Space. That's what this workshop is about. It's meant for survey level undergraduate students. So, they don't have to be science majors. It stayed at UNC Chapel Hill for a number of years, but then some local institutions started picking it up. And now we're, thanks to some NSF money, NSF really wants to see this become a national curriculum. We're currently up to 24 telescopes serving about 3,500 students per year. And Michael helped put that into perspective for me the other day. In the US, where I'm from, we have 200,000 to 250,000 students in introductory astronomy classes. So we've about 1.5% of them are using the OPIS curriculum, far more than I thought. And so that made me happy. Anyway, the OPIS curriculum we recently got an infusion of $2 million from NSF to double, triple its scope. And I have a great group of educators, and we're taking in more educators all the time. And that's the curriculum that I'll tell you about. There is a follow-up curriculum recently funded by Department of Defense, of all people, DoD, their education branch. And you may wonder, why does the Department of Defense care about introductory astronomy? But they have a real need, a desperate need for a STEM educated workforce. Defense these days, it's not just about soldiers in boots, but it's about people with technical expertise. So they threw $3 million at us, and we've been building this amazing follow-up curriculum called Astrophotography of the Multi-Wavelength Universe. You'll hear more about this afternoon because Daryl will be giving our 4th workshop on one of our more exciting projects. And the other 4 workshops, the 2 we gave yesterday, the 2 that are upcoming, are on this new curriculum that's still in development, but it's using astrophotography as a hook. The OPIS curriculum doesn't use, we try to avoid color imaging. We do a little bit because the students really want it. We try to avoid radio mapping, as you heard from Michael. Radio is a part of Skynet, becoming a much larger part of Skynet. Thanks to the DoD money, we're integrating at least 6 more radio telescopes around the world and be the first global network of radio telescopes for education. Something I'm very excited about because I've taught educational radio astronomy since 1992. And it's a very powerful tool, particularly in combination with optical astronomy, to see the universe in a different way. The OPIS curriculum does have a little bit of radio, but it's primarily an optical curriculum. It's been very carefully designed to scale. Students are working off of very carefully selected, curated lists of objects. And so they're all observing similar things. If we have multiple observations in the queue that are identical, we only dispatch it once. And in this way, we're able to scale to larger and larger groups. So OPIS is the entry curriculum, and those who like it and come back for more, we send them into the MWU, Multi-Wavelength Universe curriculum. But anyway, attend the other talks for MWU. I'll mention, I have a slide on it in here. But that was my, I was going to have the PowerPoint. Yeah, let me put the PowerPoint up for a second. I'll come back to this screen. And I'll start it up here. And I'll display settings, duplicate. Okay, and not at the beginning. Let me slide up here. Okay, so that was my opening spiel. Other than to say, you know, I said OPIS is now in 24 institutions, about 3,500 students per year. And it's the subject of a very large study. You saw some of it in Michael's keynote. Michael is one of the leaders of this study, David McKinnon, Rachel Freed, who had a poster. I'll show some of her results. May is very much back here in the corner. My grad student is very much involved in it as well. It's probably the largest study of robotic telescopes at the undergraduate level that's ever been done, and all the positive benefits that come from it. Anyway, what are we doing today? I'll slide the Zoom thing down so we can see everything. More. Hide. Excellent. Wonderful. Thank you so much. I've been teaching on Zoom for years, and had I only known. Okay, so we'll begin with a quick registration period. We'll put up that same website that was just up, but I'll make sure you go to it and you can type in your address, and we'll set you up with a Skynet account. Vladimir, who's one of my full-time programming staff, he's in the back, and he'll get you an account pretty quickly. I'll describe that in a second. Then I'll just showcase our telescopes a little bit. We're not quite like LCO, where I wasn't a former VP of Google, so I can't just go and buy tons of telescopes. It's more of a grassroots effort, but a lot of it has been supported by the National Science Foundation. I'll show you what resources we have. And one of the unique things about the network is we allow others to join us with the appropriate telescopes. I'll tell you a decent amount about the OPIS curriculum, just a teaser of the MWU curriculum, and then we're going to do stuff. You can't just sit there and watch quietly. I'm going to make you do stuff. Some samples of the activities from the OPIS curriculum. I'll show you how to submit observations on Skynet and how the results come back. Of course, it's a queue-based system, so don't expect results to come back during the workshop. Some might, because we do have telescopes in Australia, but then using data from before that I'll point you to, we'll run through some of the key things of labs 3, 4, 5, and 6. We'll do a Kepler's third experiment, a parallax measurement, since I have telescopes all over the world. The labs do simultaneous observations of main belt asteroids and measure distances. We'll do a standard candle lab. Almost all the labs have an observing component. There may also be addition of archival data, but the key thing is for the students to collect data themselves. They're very excited about that. There's a data ownership aspect to this. This is mine. I did this. Okay. Registration. Go to this tiny URL if you weren't there before, at tinyurl.com/Skynet-register. I'll stop sharing. No, I don't want to stop sharing. My bad. Can resume sharing. I want to stop my PowerPoint. Hide floating controls, lower the PowerPoint. Okay, and here we are. And it looks like, is this the right one? No, it's not the right one. Here we go. So there it is again, tinyurl.com, Skynet-register. For Heidi. The main, yeah, where we started today. Okay, you're welcome to stay. So yeah, get your email in here, and Vladimir is currently creating an account for you. Within moments, you'll receive an email from Skynet that will look something like this. It may be in your spam directory. Of course, instead of a black box here, you'll have an individualized key. And just go to this website here, the registration website, and take that key with you and type in the information. It's name, email, password again, that standard things, and type in the registration key. That will activate, that will connect you to the account that he's already created for you, and it will come for this particular workshop with 15 minutes of observing time on our telescope network, including the 20-meter radio telescope. There's also some information here if you want to play later on, and we have a finding chart that we'll use. So I would leave this page open because we will return to it. Okay, how are we looking back there? It's coming along. Okay, but while that's happening and while you're setting it up, I'll go back to the PowerPoint and give you some general information here. A few of you were here yesterday when I talked about the radio aspects of the network. I'll focus more on the optical aspects today. So Skynet has a few different categories of telescopes. The primary category is prompt, panchromatic, robotic, optical monitoring, and polarimetry telescopes. These are the ones that my group at UNC Chapel Hill, University of North Carolina, Chapel Hill, has raised the money for and deployed and maintains. Our primary site is Cerro, where we currently have 6 telescopes connected to Skynet between 16 and 32 inches. There's a polarimeter in development. That's actually May's PhD thesis. And the Chileans are developing a spectrograph for the 32-inch. So those would be new technologies that are coming along. But the other telescopes are there with basic imaging at the moment. In Australia, although there's only 2 spots here, there are actually 3 sites. One at Siding Spring that some of my team went to earlier this semester. We actually built this about a decade ago, but it was wiped out by a lightning strike. And I raised the money to replace the hardware. And now post-pandemic, we're putting it back in action. We also have telescopes. We have one at Perth Observatory and one about 100 kilometers east of there, the Meckering telescope, which is a very dark site. When they surveyed Australia to decide where they were going to put the National Observatory, this was actually very high on the list, but they went with Siding Spring. So we have really good coverage in the Southern Hemisphere. Up north, we've consolidated our telescopes at Darrell's site. Darrell's in the back there. Though the telescope that Martin has sent to Darrell is now sending to University of Arizona, and it will be relocated to the U.S. Southwest, Mount Lemmon, which is a very nice site. So these are the ones we're most responsible for. Then we have our partner telescopes. Anyone with a telescope that can be controlled remotely, meaning you have a weather station, and you feel safe operating your telescope from a remote location. This is a little out of date. Some telescopes go, more telescopes come, and you can use our scheduling interface, which is we've been using the same scheduling front end and back end for about 10 years. For the past year or 2, we've been building Skynet 2, which is going to be a truly fantastic thing. It's going to treat the optical telescopes and the radio telescopes fairly equivalently. I talked yesterday a bit about how making radio astronomy more like optical astronomy is a great pathway for our students who have an intuition for optical astronomy to transition into this other realm that they usually don't have much access to. And then we have our radio telescopes. I'll go by these real quickly because that was the subject of yesterday's workshop. We've had this since the Great Recession. You all from around the world call it the global recession, but us Americans, whenever anything terrible happens, we call it great. So it's the Great Recession for us. Got about $100 million of stimulus money from that and refurbished this telescope at Green Bank Observatory, 20 meters across, 6 stories tall, 150 tons. I really got to get a webcam on this because I think the students will be very excited to see it move and not just recover data from it. As part of the DoD grant, we're integrating more. These are the University of Tasmania telescopes that will be added very soon, within the next year or less, going all the way up to 30 meters. And the 14 meter, I have half the time on. All these others, it's between 3.5% and 10%. Also part of the grant will be integrating 2, maybe 4 telescopes from North Carolina, used to be a NASA tracking station, and Arecibo's education telescopes on board as well. And I know others are in the wait. Darrell back there has some smaller ones that he wants on the system as well. So I'm very excited about opening this new window for students that they simply couldn't access before because individual institutions can't afford to maintain these. Our mission is split 50-50 between research and education. We started out as a research system, primarily for gamma ray burst follow-up, but now someone somewhere every 20 days is publishing Skynet data in peer-reviewed journals, multiple times in Nature and Science, leading tracker of NEOs in the Southern Hemisphere. But we're also very dedicated to our education efforts, education public engagement. And this slide's a little out of date. It's closer to 50,000 students that I know of at this point in time. Lots of instructors set up groups in Skynet and populate it with accounts, and they're doing education as well. I just haven't been able to track it. We have 4 large programs, and I'm here to talk about the ones at the undergrad level. So let's start with OPIS, which is the topic at this workshop. As I said, it's now expanded to 24 institutions, 3,500 students per year. We have the capacity to go 10-fold more. And I'm looking for new institutions as well for the next round of grant writing. We have about $2 million from NSF, most of it fairly recent. And howdy. And there's money for instructors. to train on the curriculum. Every fall, we meet once a week and go through a different lab every week. And, you know, this is kind of like what CLIA has evolved into. A lot of you are familiar with CLIA, where it's all simulated here. You're doing similar kinds of things, but the students are collecting their own data. Anyway, we train you. There's some funding for feedback once during the grant cycle. And the key thing is surveys. We're carrying out the largest survey of robotic telescope use at the undergrad level, and Michael Fitzgerald and others are playing leadership roles in this. You also get a site visit from Rachel Freed. If you haven't met her yet, she's the bubbly one running around. And the site visit's not to judge you, it's just every single implementation of OPIS is different. You don't have to do all the labs. Different people do different subsets of them in different ways. And for the sake of the study, it becomes an apples to orange comparison. So we have to send someone in to collect some firsthand information. But it's usually quite fun. She'll do a round table with the students as well. Again, survey level, this was designed to work in classrooms of hundreds, but it also works down at the very small level. And there are currently 8, soon will be 9 labs. 7 of them are Skynet-based. We took the approach of what should they be learning. For this, we were using small telescopes at night, our local planetarium, doing things that did not really connect to the lecture curriculum that's typically taught in Astro 101 courses. You may have these similar experiences. We can take students out at night to work with small telescopes. We can put them in a planetarium, but then we take them back to class and we teach them about rotation curves and the Great Debate and in Kepler's third and things they're not doing in lab. The goal here is we're building the technology to be so reliable. We're building the software tools to be so reliable that survey level students can now do these things. After we did this, we had to redesign our advanced observing course for majors on campus because the survey, hundreds of survey students of all disciplines were doing more than the advanced astro majors. So you can now, these survey students can now do exactly what they're learning in class. The theme is our place in space. That's one way you can organize introductory astronomy, the lesson that we keep learning that we're not at the center of the universe. We have an exercise on Venusian phases, the Great Debate of 1920, Hubble's law as well. We're adding a new lab where they'll actually measure Hubble's constant with radio spectra they collect. And the backbone of learning our place in space is the cosmic distance ladder. They start early on with size measurement of the Earth using globes. That's one of the 2 non-Skynet-based labs. But then parallax and standard candles are Lyra's Cepheids type 1As. Along the way, we get Kepler's third and a rotation curve for the Milky Way using radio spectra. Okay, and we won't be able to go through all of it, but that gives you an idea of it. But again, as I was saying, we sat down and said, what should they be learning? And what's the best tool for this? Not what is the tool that we happen to have? What toy do we have that we can play with? We have some small telescopes, we have a planetarium. Yeah, you can do stuff with them, but it may not reinforce the curriculum. Here we said, what do we need to do to reinforce the curriculum? And 7 out of the 9 times Skynet appeared to be the answer. And when we first deployed this in 2009, you can tell from the old Facebook style here that this is older. We were kind of surprised. Students started posting, not that we're stalking our students on Facebook, but these were brought to our attention, posting stuff like most exciting homework anyone will ever do. And pretty damn awesome. They went ahead and started making color images all on their own, even though Afterglow at the time wasn't designed to do that. How often do you sign a homework and that's the response, that they're posting it on social media saying pretty damn awesome? So we knew we were on to something. And this also showed up in the numbers. Over about 5 years, our enrollments went up 100% in all of our intro astro courses. Our astro track majors went up 300% from typically 10 in the program to 40. And this paved the way for us to make new astronomy track hires. Often that's the only way to get a new astronomer at your institution is to have a teaching need for it. And as I said, we have since expanded, and I just have a little blurb down here about the video tutorials because I don't have any other place or time to talk about it. But shortly before the pandemic, quite fortuitously, I filmed 65, typically 10-minute video tutorials, walking through all the different aspects of how to do this or overviews of the labs. And they've proven quite popular. We've learned students don't like to read, they'd rather watch the instructions on a video. And these get about 500 views per day during the semester for over 30 hours viewed per day, which means I'm teaching more than 24 hours a day, which is kind of an interesting thought, but I still get to sleep. And Rachel just took down her poster. This poster was up yesterday. We have a great education research team. Michael Fitzgerald, David McKinnon, Rachel Freed, May is learning from them, and others, Tim Spuck, who's here. And they're starting to publish the results. The first thing we focused on was self-efficacy and exploratory factor analysis, confirmatory factor analysis. I used to not put any credibility in education research methodology until I started working with this group. And I realized it can be done quite well. I still believe most of the time it's done quite poorly, but if you have the right team, it can be done quite well. And once you have confirmed the different instruments you build, this one's on self-efficacy, which is students feeling that, yes, I can do this, which is certainly a prerequisite for whether they're going to go into a STEM field or a STEM career. If they don't believe they can do it, they're not going to do it. It's a necessary but not sufficient condition, but very important. For decades, the focus in education research has been exclusively on learning gains. And that's, of course, important. But if they hate the experience so much that they don't come back for a second class, their long-term learning gains are much less than they could have been. Things like self-efficacy, things like attitudes and belonging in a STEM community is very important. Anyway, these self-efficacy gains are off the chart good. These slopes, to put in context, this is the number of standard deviations you're pushing your class from the pre-test to the post-test. And typically results around 0.5 are typical and decent. If you get 0.5, 0.6, 0.7, you're pretty happy. 1 is consistent with mastery learning, totally master a topic before going on to the next. 2 is consistent with one-on-one tutoring. And the holy grail is, can you achieve 2s in a mass-produced environment like this is? And with self-efficacy, we're getting there. We're between 1 and 2. And in some of our institutions, like Daryl's and like mine, we are sometimes getting 3s, which is just unbelievable. The 2 measures are their confidence in their scientific knowledge and their confidence in instrumentation. But the kind of the cool secondary result, which I think Michael mentioned this morning, those lines are for males and females, and they come in with the well-known gender confidence gap. And after exiting this curriculum, it's gone. Almost done with the spiel, and we'll get to work. Just a little teaser for MWU, Astrophotography, the Multi-Wavelength Universe. It's not a course on how to make a pretty picture. They certainly learn how to do that, but it really is a physics-oriented course. The astrophotography is a hook, but there's calculation, physical interpretation with each of the modules, and you can go to any of the other talks, including Daryl's this afternoon, and we're having one on star-forming regions tomorrow, where we really get into the details of astrophotography. $3 million from DoD, and there's $9,000 for participating educators. You just have to offer OPIS once and then get in on this. Some of that money's gone now because we're about halfway through. And it's primarily, not exclusively, but primarily for students who took OPIS and decided to come back for more. This is a seal the deal experience based on a field program I've run since '92, where everyone comes back super excited. They become STEM majors. The goal here is to get that in the classroom using the remote technology of Skynet. And since it's usually a smaller number of returning students, you can give more time per student. And the theme is color. All sorts of ways of using color to draw physical implications and on light producing mechanisms. So typical second semester stuff, but come to another workshop for more of that. Okay. The blathering part is done. Do you all have your active Skynet accounts set up now? Okay. How about you open these websites? The last one is just the one you already have open. It a finding chart and some few things that would be useful. The first one is the observing scheduling site, skynet.unc.edu, critical. The second one, if I can copy these and put them in the chat as well. I can try to. For the online participants, I'll do that. You're on it again and put those in there. Excellent, thank you. So I'll restart this. Skynet is the observing site. This is the last year for this version of Skynet. Skynet 2 is getting closer to reality every day, and it's probably going to be, it's just going to be the most impressive interface. It's going to be very modern. Afterglow is something we're very proud of. It's online astronomical image reduction software. We're continuing to add to it. It's probably going to become the replacement of Astro Image J. At least for the optical data you take with Skynet, it's already there. No downloading and then re-uploading, and no installing software in lockdown systems, which is often the case in high school. Just a web environment. And the third one is a group activity we're going to do where I'll guide you through it when the time comes, but load that up because you'll claim an image or two and do the analysis yourself. We're going to do basically a student lab in moments through crowdsourcing. I'll leave it here just for a moment. Does everyone have these websites up? Does anyone not yet have all these websites up? Let me do it that way. Okay, so the time has come to do things. Let me close down the PowerPoint. The first thing I'm going to do is show you how to use Skynet. And so go to skynet.unc.edu. It'll look like this. Again, it's about 10 years old. The new framework is much more modern. Can't wait to roll it out in about a year, but this certainly functions. It's serving 3,500 students per year, plus all of our professional users. And I'll give you just a quick tour here before we put in the observation. One of the cooler pages is Skynet Live. It shows you what's connected at the moment and the status of each. And often telescopes drop off during the day, but they reappear at night based on local energy constraints. This one's in Australia, and so that's being used right now. Most of ours are on this side of the planet, and so you can see from the sun elevations, they're just waiting. One of these, this one here is in Poland. Okay. Over here we have telescope sites with, let me go to Tololo, and there's information about each telescope. Maybe I'll go to prompt 6, and you can see the filters and field of view and webcams and recent images and things of that nature. But we are going to go to my observatory. When I go here, I have many extra things because I have administrative level stuff. Once you have a group of students, we create, you get down to group management, you become a leader of a group, and you'll be able to add your own students in the group. But right now, let's just go to optical observing, the first one, and you click on it. Hello, internet. Oh, one of the poor features of the old site is recent images. It will load them up before it will let me move on. And so when I came here to prompt 6, it's insisting on showing me the last 5 prompt 6 images. Good, they're in, okay. So optical observing, and you may not have anything here yet if you're new to Skynet, but once you put in observations, they will reside here. You can see when they're active or complete. Optical observing, and then you go to add new observation. Over here on the right, second one down. And it brings up a little viewer. We call this our Sky Viewer. The Skynet 2 version is basically Stellarium. We have rebuilt about 50% of Stellarium ourselves, and it's in the viewer and does some amazing things. So just hinting as to what's to come. So let's put in a picture of Saturn for starters. With the OPIS curriculum, we start with just kind of In the first lab, the students take a bunch of pictures of solar system objects. It's more to learn the skills, which they'll then apply in the later labs. So let's look up Saturn, because it's an observable planet right now. Here it is. Let me hit the now button. And it's not, okay, it's up late at night. But so we'll put it in, and tomorrow your observations will come back. When you press that, it fills in the coordinates, and it will update the coordinates for known moving objects before dispatching. So you don't have to worry about that. Often with the students, so what about these numbers here? You can set them as I have mine. This is good for bright planets. Often with students, we don't wait to -18. That's when the pros start, when the sun is 18 degrees below the horizon. But with the students and bright targets, we start them at -12. They can crank out a lot of stuff before the pros get too involved. Min target elevation, 30 degrees up. I like to check my air mass chart. And yeah, in my southern hemisphere observatories, Saturn is going more than 30 degrees up, so that will be fine. Moon phase 100, as long as the moon's about 30 degrees away, Saturn's going to turn out fine. If you're imaging something fainter, you may have different moon constraints and moon separation angles, but this is a good combination for Saturn. We have other things like dithering and pointing offsets. We can ignore this now. Bright planets will be offset automatically. You can actually see it put a 2 arc-minute offset, and it's because it's so bright. We want to keep it off the center of the chip. That's where the science takes place, and bright things leave a residual image for about 20 or 30 minutes. Okay, I think that's it for this page. There are all sorts of advanced features, orbital elements and whatnot. We can just hide that in the accordion feature. Orbital elements for like asteroids and things of that nature. Okay, let's go. Everyone good? Everyone ready? Let's pick our filter next. Yes. Let's pick the filter first, and we'll come and pick the telescope second. One of the nice things is you design your observation, and it can go on many telescopes. You don't have to pick just one. If you pick just one, what happens if it goes down? So we often have the students design their observation. It will say, okay, for what you want to do, here are 6 telescopes that can do it. And often they'll select all of them, or they'll select only the prompt telescopes for a guaranteed better result. The non-prompt telescopes, some are quite good, but some are downtown campus observatories that you may not want. Okay, and in the sign-up sheet, I have recommended filters and exposure times, and you don't have to go there. I'll just tell you. It said for Saturn, B band is good for looking at Saturn. And if you want to maybe saturate Saturn a little bit and bring out more of its moons, high through is good. And you can select them both. And as you select them, you'll see we lose some telescopes that don't happen to have both of those filters. What's left here, these are the telescopes that can observe the target you selected. And only southern hemisphere telescopes could observe Saturn high in the sky. So my list has already been truncated. Then when I selected filters, it's truncated again, but there's still many telescopes that can do it. And so once you've done that, and you can see we have every filter system imaginable. We had custom filters made for many of our telescopes that hold 17 filters to get as many filter options on as many scopes as possible to reduce bottlenecks. So save and continue, and now we'll do our telescope selection. And one thing you can do is just press your orange button. I have multiple time accounts, but you probably have one. The little orange button selects everything, but you may want to go through and unselect non-prompt telescopes if you want to guarantee yourself a high quality result. The RCOP is in Perth. It's not one of ours. It's okay. But the Tololo scopes, the Meckering scope, and some of your accordions may be closed and you can just open and see what's there. I would select all prompt telescopes that your orange button permits you to. And when you're done with that, save and continue. And we're at our exposure screen. And the way this works is we're going to design the observation for a generic telescope, a 16-inch back illuminated telescope at our primary site, Tololo. But then it can go through on whichever telescopes you just selected that's first available. each telescope has different efficiencies, different throughputs. And so you don't want to design a separate observation for each. So under choose exposure efficiency, select the generic telescope. And then your two filters, mine are already loaded because I just practiced this observation before the workshop. But to make one of them high through, one of them B band. That filter said B band, 1 exposure, 0.3 seconds, high through, 1 exposure, 0.03 seconds. You'll get similar results. Go ahead and stick them both in. And as you slide to the telescopes underneath, you can see how the exposure time is going to automatically scale. We know the efficiencies of our telescopes. We know 0.3 seconds on this scope. If I want to get the same signal to noise on this other scope, what do we need to do? And it charges you the same number of observing credits. When you signed up for your account, you got 900 credits today. Each credit's a second on the generic telescope. And so you can see what you'll burn. Now, anything less than a second will be charged a credit. It rounds up. But if you're happy, then you can come down here. There are advanced features, like if I wanted to repeat this observation 14 times with 1 day in between, like if you want to watch moons go around, you could do that. You can do that. In fact, let's just do that. I'm going to repeat this up because that's what the students do in Lab 3 that we're about to do together as a group. I'm going to repeat this observation 14 times with at least 1 day in between. And so day after day, you'll collect observations. If your telescope goes down due to weather, it will just wait for the next available in your list. Let's try that. Other things, you can delay the start and all sorts of features here that we don't need to go into right now. Save and continue. Checkout screen. Come on, internet, there we go. And I got impatient and kept pressing buttons. I'm gonna go back one screen. After you check out, it will take you here. We're having some internet hiccups. I'm just waiting to get back to the observing page. Come on, internet. There we go. And so you see my observation of Saturn is active, and we'll see over the next 14 days, observations come in 2 at a time. Here's one I put in previously, and you get little previews. That's Saturn through the open filter. So high through, I didn't define it. High through is any of a collection of filters that let through a lot of light. B is, of course, the B band filter. And so I can click on any of these, and here it is. But Skynet is not really the place to look at your images. But you submitted that, and that will be coming back. Everyone good there? Okay, basic observation in Skynet. So now let's switch over to Afterglow. This is our image processing suite. Put the people down here at the bottom. Okay, and go to afterglow.unc.edu. It'll make you log in. You can log in with your Skynet credentials, and you'll get to a page like this. You probably don't have anything open at the moment, but I'm going to take you to a picture of Saturn. So if you're here, we're going to open files. That's the folder here in the upper left. Click on it. You will see something like, excuse me, I got the hiccups. You'll see something like this. Sample images will be going there in a second. That's where I put the images we're going to process today. Your observations will appear under Skynet. Once they come back, Skynet user, your observations will be there. But anyone in your group or collaboration, you can gain access to their images as well. We're going to be putting in constraints that for the pros, their images will be hidden for a year, but educational stuff available immediately. But anyway, go back to files. You also have a workspace. You can upload images of your own or save work in progress. There's a gig of space there, so it's not a permanent repository. But let's go to the sample directory, slide down to workshop, and slide down to Saturn. Since we just put in a picture of Saturn, this will give you an example of what comes out. There should just be one picture there. Is taken in a luminance filter, which is a high throughput filter like open, and open it up. And I think I actually have it open already. For you, it'll be the only thing open. For me, here it is, down at the bottom of my list. And okay, so here's the picture of Saturn. It's a Google Maps kind of interface. You can drag and zoom into any location. And Saturn's under the blur. You see lots of moons and background stars. Let's do some basic brightness and contrast. I'm showing you the basics. Again, this is the introductory lab of the introductory sequence. So we're learning to crawl before we walk and run. Go to this upper tab here. This is display control, display settings. And try something just like hitting bright target. That will change the brightness and contrast. And so you can see just the planet Saturn. This was taken a little bit of time ago. You can adjust. If I go here to the saturation level and maybe take out one of the 9s, you see it got a little closer to saturated, take out another, and zoom out. And so you can adjust the saturation level, maybe 99.5, 99.7, you know, shrinking the glow of Saturn light bouncing through our atmosphere to hopefully bring out some more of the moons. And I have a little snapshot from Stellarium here, taken at the same time. So what do we have? We have Rhea, Tethys, Titan, Iapetus, and Rhea, Tethys, Titan, Iapetus. And so in this introductory experience, they go through. There's a third tab down is a marker tab. If you want to play a little bit, turn on centroid clicks, and I think that one was Titan. Click on it once, it marks it. Click on it twice, you can label it. So students can do some moon identification. And let's see, this was under the, you all showed me how to hide this thing. And down here, you can do like a screenshot right there. It dumps it out, and students can then upload this into the labs are offered through Cengage Learning, where some of the funding comes back to pay for the telescopes. And they fulfill their assignments and upload their images. And the nice thing is when they do that, it actually wrote their name into the header, the EXIF data. And so you put an EXIF viewer in your browser, and with one click, you can do a cheating check to see if they actually did it themselves. Very basic stuff. Questions about that so far? Okay. Oh, the marker thing is the third tab from the right. You click on something to get a marker, click on it twice, and you can do a label. You can make the label bigger. You can move the label around. But in the interest of time, I'm going to pop on to the next thing we're going to do. So this is an example of something they do in Lab 1. They also find dwarf planets. They learn how to compare to the DSS, all sorts of things. They learn a toolkit in Lab 1. Let's move over to Lab 3. Lab 3, we just put in a sequence of observations of moons going around Saturn. I'm going to point you to observations of Triton going around Neptune. And we're going to do a Kepler's third activity, and we're going to crowdsource it. Those of you online, those of you here, I'm counting on you to join in, not just sit there and do this. So the other web address I sent you to, I think it was tinyurl.com/Skynet-Triton, sent you to this web page. And pick one. So we have 14 observations that I've already taken. I'll show you where to get them in a second, but claim one for yourself. I'll claim 2 there, if you would be so kind. Let me check the time. This goes to noon. We're doing fine. Claim 2 of them. I'll claim 2. Let's see if this gets everyone. So we're going to do one of these tasks that we have our students do. And if anything's missing, I have the answers on a little spreadsheet and I can pump it in there. So we got all but 2, not bad. Okay. And if anyone else wants to grab 21, 23, great. Now, check your numbers. For me, it was 1 and 3. And so you find your numbers. And we're going to go back to Skynet. And we're going to open files. And we're going to back out to that workshop directory. And down here, there's a folder called Triton. Open it up. Find your 2 images. And bring them in. For me, it was 1 and 3. So I'm going to open those. I'm using there's a filter over here. So if you have a bunch of files open like I do, I can filter on just the files I want to see. So the reason we're doing Triton going around Neptune is there's only one moon you can see, and that's Triton. And so that way we can skip the moon identification stage in the interest of time. But the students, some pick Jupiter, Saturn, Uranus, Neptune, whatever is available. They all have pluses and minuses. Some are prettier, some are easier. This is the easy one because you don't have to do moon identification. But you should be able to find Neptune and Triton pretty easily. There's one of my images. Here's the other. When I click on it, it's importing the stuff over. Neptune's bigger, brighter, and the little thing next to it is Triton. Okay. Now on the web sheet, it wanted to know what telescope took this, when did it take it, and what's the distance between the planet and the moon. And so if you go to the second tab, that's an information tab. Let's get some of that information. And so I got to keep sliding y'all around. But here's basics. And if you want more information, there's the full FITS header right there, but we don't need that right now. For the telescope, it's here. So for this image, it was prompt MO. That's measuring. And let's take the center JD as the time. Forget the units, but just grab the Julian date center. These are short exposures. You can grab Julian date start if you want. But grab the Julian date, grab the telescope, and let's populate this spreadsheet. Don't really need the telescope for the analysis, but it's always healthy. Yeah, and put your Julian date in column D. Separation in arc seconds, I'll show you how to measure in a second. What we're going to do is make a plot of how far is the moon from the planet as a function of time. And then I'll show you some of the cool little graphing tools that we've built, graphing, modeling, analysis tools, and you will model the orbit. So I'll give you a second to get the times in there and the telescopes. A lot of these were taken with prompt 5, which is at Cerro Tololo. Prompt Meckering is one of our Australia scopes that's been working for a while, and Daryl actually manages it from Canada. Oh, I have another. I'm just sitting around waiting for you. I have another that I need to measure. Prompt 1, no, prompt MO1. Here's the Julian date. Let me copy that over. Okay. See, in the end, everyone claimed a pair of sources, so this is good. I'm not going to have to go to my backup data set. IMAD, Ahmad. Oh, there. Okay, that's okay. We'll continue, not a problem. And now we need to measure the separation. So let's go back to Afterglow. And this is the 4th tab down. You see, we have lots of tabs. We do lots of things: photometry and batch photometry, alignment, stacking, advanced pixel operations, all sorts of. This is a pretty powerful tool. But we're just going to go to the 4th one down. It has a little graph. It's called the plotter. And zoom in on your target. Make sure centroid clicks is on, and we also have planetary centroiding. Planetary centroiding is a different algorithm than centroiding on a point source. Right now I have planetary centroiding off, so I'll click on the moon, and you see I have a little measurement bar now. I'll come over here, then I'll turn planetary centroiding on, and I'll click on the planet. Try to get close to the center, but it will perfect it. And then if you slide down, you have the distance there in different formats: pixels, arc seconds, arc minutes. I think we want arc seconds. Now I'll just copy that number and I'll put that in the spreadsheet. So that was my first one. And for my second, there it is. I got planetary centroiding on, so I'll start with the planet, turn that off, and then do the moon centroiding. Now it's farther away. Now Triton's orbiting Neptune almost face on. If it was face on with the circular orbit, we wouldn't see any difference, but it's not quite face on. So we will see apogee, perigee, or apotriton, paratriton. Now I'll give you a chance to get your numbers in. I'll bring up my cheat sheet. I'm going to help you, Maud. Give you a moment to measure your second one as well. And you can already see, looking at the numbers, there's variation. Once we get them all there or close enough. Oh, Ahmad's caught up, so now I feel guilty. I just put your answers in. Does anyone else want an assist?
Yes, I do, Mark. My computer doesn't, so the website is not responding anymore, so I can't really measure.
Okay, I gotcha. So Mark is 23. Here are two numbers here. What happened? We just lost the entire. No, I fixed it. It must have been something I did. There's Mark and another Mark. So number 7. Let me grab that one. And just to be careful, I'm going to copy and paste as text in case any of it's in some funny string-based format. Paste, special values only. Okay. Now, the other site you opened was the graphing tool. It was tinyurl.com/Skynet-graph. You can see there are lots of tools for all sorts of things. Let's go to the moon tool and grab that data, the data that I just copied and repasted in text format so we don't have any problems. Copy it, come to the table, paste it, and there's the data we just measured. And so what are we looking at here? On the x-axis, it says X, but we can enter what that is. Julian date, measured in, I believe it was in seconds. The y-axis is separation, measured in arc seconds. Give it a title if you want. Separation of Triton from Neptune. Separation. You know, just an example showing you how students can fill in the axis labels. We could have done that for them, but it's a good exercise for them. Now we do a little bit of chi-by-eye modeling. So I like to, you can see we have a semi-major axis, we have a period, we have a phase, we have a tilt. I like to drop my semi-major axis to kind of get near the top of the data. Maybe shift the phase to kind of go through the first one. shrink down that period until all of a sudden, yeah, right around there. It's pretty good. And so what we're plotting is how far is the moon from the planet. And with some moons, it crosses the planet, but this is like an absolute value. In this case, we're not crossing the planet. We're just going around it, sometimes closer, sometimes farther. And so the tilt is really important in this case. You can bring it up, and I've done this a lot, so mine looks pretty good, but hopefully you're all getting to a similar state. And I'll let you do that, but as you're doing it, what you just measured is the semi-major axis in arc seconds. So there's some math the students have to do, and the lab walks them through that. Again, survey students, so we hold their hand through the mathematical calculations, but we do have them do mathematical calculations. And so they end up putting that in AU, and the period they put in years, and then use Kepler's third, which puts out the central mass and solar masses, and they convert to planetary masses. You could also do other units that put it in planetary masses. But is the modeling making sense? Nice, simple tool. And some of the modeling tools we built are much more involved. Again, come to Daryl's talk this afternoon. And you can paste right over top of the old one. Or you can copy the old one, delete it, and then paste. What I did is I copied my data, and then I put my cursor in the first square, and I hit Control V, and it just overwrote everything. And I had more lines than the garbage data. There's some garbage data in there to start always. You can delete them. Okay. And yeah, one bad point can really throw you off. And so it does require walking around the classroom, looking at the students' results, or the students helping each other, working in groups, that kind of thing. And again, you can save the graph, and it pops up the honor pledge, which is written, it says it's an honor pledge, but it's written in the EXIF data. And so you can view that EXIF data if you have an EXIF viewer, which I do, but I'm not going to go there right now. Okay, that was the Kepler's third activity. Oh, and as I was saying, they calculate the mass of the central body, Newton's form of Kepler's third. We go till 12, right? Okay, all ready to try something else? Okay. Lab 4 is parallax. And we won't go through the observation. That observation's a little tricky. We don't let every student do that one. One representative does that for the whole class. You have to do a little bit of planning because it has to be an asteroid that's observable in the south and the north simultaneously. I grant the instructors target of opportunity access, which is the highest priority level. So you can take over the telescopes when you need them. And both telescopes run a sequence of like 10 images, because it does take time for the telescope to slew into place. The start times may not match perfectly, but as long as one image from both telescopes overlap during that period of time, you could do parallax to a main belt asteroid. So let's go back to Afterglow and open files, go to the workshop, and at the very bottom, there's a folder called Parallax. There are two pictures, and there were a stream of, one of these is from Prompt 3 in Chile, one is from Moorhead Observatory in downtown Chapel Hill. There were a stream for each of these, and we've pulled out two that are close in time. The students do that themselves. Open those two. I probably already have them open. And I'm going to get rid of my filter. This asteroid was Fortuna. Okay, so there they are, and you can take a peek at each one. When you click on it, it loads. And so this is from downtown Chapel Hill, and the other one is from Chile. I'll let that load. And a nifty little trick you can do, if you come over here to the gear on the left and turn on sync orientations, it should default to sky. That way, as you go back and forth between the two images, they maintain the same relative position, which is a nice bonus. You can essentially blink between them. And I don't know if you can find the asteroid that easily. I see it. And I'll help you out here. It's that one. It's the bright one kind of in the middle, which makes sense. The telescopes were told to point at the asteroid. If you zoom in there and blink between them, you see the motion. And these are simultaneously. You can check the timestamps under the second tab if you want. So that motion is due to parallactic shift, viewing it in Chile and North Carolina simultaneously. So for here, I'm going to show you, there are all sorts of ways you can do this. And we have split screen capability and all sorts of things. I'm going to show you alignment and stacking. Normally used if you're trying to make a deep image, but here we're going to use it for a parallax measurement. So come down to the aligners, the third from the bottom. And select your two images. You can either find them in the list or you can filter. Again, over here at the top, I have a bunch of stuff in my list. But if I type in Fortuna, it limits it to that, and then I can just select all. Otherwise, you have to hunt through this list and find those two, Fortuna Moorhead, Fortuna P3. And we are going, it doesn't matter which is the reference. I'm going to pick P3, better telescope, better sight. And make sure all these are on. Crop, enable rotation, enable scale, enable skew. They're taken with different telescopes. They can have different rotations and plate scales. And the mode that you want is WCS. Both of these images have a WCS. Though you can see we have multiple alignment modes. If you attended May's workshop yesterday, the feature-based alignment is how we align pictures of the moon. There are other alignments for planets that don't have any background stars, but these all have a WCS. So you pick WCS, make sure everything's highlighted, and submit. Which only take a second. So they each have a WCS. It will line the one up to the other and crop them. So they're exactly the same. As you go back and forth, you got to reload it. But as you go back and forth, they're the exact same size. And you can see that asteroid a little bit more easily in the center. But let's keep going. Well, I'll pause. Are you aligned? Everyone aligned? Good. Pretty painless to align the data. Next tab down is the stacker. And you want to select the same two images. And there's lots of stuff here that we're going to ignore. There's outlier suppose you're stacking a bunch of images to make a deep image. There's outlier rejection to get rid of hot pixels. There's smart stacking to get rid of images where you just had a cloud. There's all sorts of really cool stuff here. All this equalization is if you're doing a mosaic, trying to get the panels to line up. But all that you really need is average, everything else turned off, and turn on propagate mask. If you were doing the mosaic yesterday, I don't think you were using any of this anyway. So pick your two, average, no rejection, no scaling, no smart scaling, no equalization. Propagate mask just keeps that cropping the same. And then we're going to submit, and it will create a new file. And there it is, Fortuna. Fortuna stack. It uses the name as much as it can until the two names differ, and then it just adds underscore stack. So let's load the stack. And we're going to adjust the brightness and contrast to really see the separation there. So once you have your stack up, go to that first tab. And you may want to hit bright target. That's too much. So under saturation, I'm going to delete some 9s, maybe delete another, and there it is. That is the same object, you just see it twice. because it was taken from different hemispheres. And so we can use the same measuring tool that you just learned about, fourth tab down. Centroid clicks on, not planetary centroiding, but centroid clicks on, and you click on one and you click on the other. And I just measured the parallactic shift. It's down here, 5.437 arc seconds. Now I'll give you a moment to get there. And we're not going to do the math today. And we are making a critical assumption that our baseline from our two telescopes is perpendicular to the line of sight to the main belt asteroid. You can, of course, be fancier and have the trigonometry in there, but the introductory level, I don't think that's helpful. And so that's a source of error. And we just do a standard parallax equation, assuming the line of sight is perpendicular to the baseline between the telescopes, and they get a distance that's good to a factor of small to the true value. And really, we're just checking, is this a distance in the main belt? And if so, we pat them on the back, and then they go on and do parallax to Alpha Centauri with archival data. And actually, before Alpha Centauri, we have them do parallax to Venus and measure the AU. And then we do stellar parallax to Alpha Centauri. So this lab has repetition in it, but it's the good kind of repetition, reinforcing the skill set. So y'all get that. Okay. Again, this is the introductory sequence. So these are simpler activities. But the key thing is, without Afterglow, if you just gave your students a handful of images in FITS format, survey level, non-STEM, would they be able to get here? Probably not, or not without great difficulty. Yet we're doing it within moments because we built the tools to make it possible for them to do it. And this, you're teaching them parallax. This is what you're teaching them. And now they can do it instead of just listen and hear about it, or have some setup in the room, right? They can do it with astronomical data. Though in fairness, when we do this lab, we do take them up on the roof and we do a physical parallax to a nearby water tower and smokestack. So they get that aspect, and then we do it astronomically. Again, check my time, still doing good. So the next lab is standard candles. We do R Lyraes, we do Cepheids, we do type 1As. The R Lyrae data set, they collect themselves. The Cepheids, we could do them like in the Magellanic Clouds or something, but the idea is to get farther and farther and farther. So we do a nearby galaxy. It's like the only nearby galaxy where you can see a Cepheid. It's the one Hubble used. Well, no, he of course found the Cepheid in Andromeda. Ignore all my history and my statements, but there are very few Cepheids you can see with small telescopes outside of the local group, and we do one of those. I think I'm right in that statement, but I'm not a variable star person, so forgive me if I'm wrong. But the point I was trying to make with that is, since it's far away, to see it, luminous, long period archival. So the Cepheid is archival because it's a 60-day period. It has to be for us to see it with our small telescopes in a faraway galaxy. And we do type A's. For a while, we were one leading discoverer of type A's supernovae in the south. Of course, things are more automated now, but those are unpredictable, so that's archival. But the R Lyraes, they do themselves, and then it's that good kind of repetition. So let's load an R Lyrae data set. If you go to Open Files, Workshop, and we're looking for NGC 1261. And there should be 50 images there. Just load them all. Grab them, load them all. It'll take a moment. I have mine already loaded. If you want, once you get them here, you can filter on NGC so you don't see the other stuff you have going on. And I'll just pause. If I were loading them, I'd know how long it takes you. Depends on the internet of the room. It shouldn't be too bad, though. Just give me the signal once you've loaded your 50 NGC 1261s. That fast, great. It's loading the header image information. you don't actually load the image like until you click on it. So here it is. If I click on the next one, see, it took a second. That was the FITS file being transferred over. We don't transfer the FITS files over until we need to. Anyway, go to the first one there. And in the sign up sheet, if you scroll to the bottom, I'll put it up here. I gave you a finder chart. I have to find it. I have to find the finder chart. Here it is. And so here's our library. It's a glob, of course, globular cluster. Here's the reference star we're going to use. There's a bright star. So I'm going to help you. If you watch, I mean, you can, of course, go back and forth between this image and this image and try to figure it out. There's a rotation here. Let me help you. If you go to display settings, top tab on the right, and scroll to the bottom, move the zoom controls, which I keep hiding, but there's a rotation. If you click it 3 times, you'll be in the same orientation as the finding chart. You got the glob, you got the bright star, and our stars are over here. This is a ghost of Jupiter. Someone observed Jupiter before this and left a little residual signature. Anyway, if you get in this configuration, I know this by heart. This is the RLIRE, and this is our reference. And if you go to the photometry tab, which is the light bulb, the one with the light bulb, let me clear out what I was practicing beforehand. And let me make sure I was doing all sorts of things beforehand. I'm just gonna check, yeah, my settings are good. Okay, and so it's this one right here is the RLIRE. Use your finder chart if you need to. And just click on it. And this slightly brighter one is the reference star. You gotta click on the right stars for this to work, at least for the RLIRE. Got the glob, and it's like a pair of bright ones. I clicked on something else by mistake. I'll delete that. There's a pair of bright ones. Here, I'll hide the apertures to help you out here. A pair of bright ones and an angle pair of fainter ones. It's the ones in the middle. RLIRE, reference star. You got them? Find them? Good. You're all pros. Students, though, it will take them a little bit longer. They're not as good at this skill set. Here, I'll turn my apertures back on. And when I clicked, it did photometry. And don't do this right now, but I'm just going to show you real quick because it's cool. Under settings, that was basic constant aperture photometry, but we also have adaptive. I'm going to set it back in a second. Adaptive's a little slower. Vladimir, who codes the back end, he's one of the experts on all sorts of photometry. If I go down, I know image 4 is a little streaked. And isn't that lovely? The adaptive photometry adapts to wind streak conditions. If you're trying to combine data from different telescopes with different pixel scales, the adaptive can be quite useful. But these are all from the same scope. It's faster to go constant, so I will go back to constant photometry. And it's hitting the server, and as it hits the server, it pulls up flux values, but here are the magnitude values, and this is all relative. There are options up in the settings to calibrate it to OPIS and have calibrated photometry, but this is a relative exercise. So what you want to do, you can click on any image. It's already found them. It'll photometer them. And so what you want to do is select the images. So just filter on NGC, so none of your other images are there. Hit the select all button, so you don't have to hit this 50 times in there. And select, oops, I turned one off. Selects all of them, and then hit the little button here, and it will photometer both of those stars and all 50 images. Done. It was that quick. Be a little slower when Daryl presents this afternoon, because you'll be doing like 4,000 stars and 4 images or something like that. But it's an Excel spreadsheet. Did it all pop up for you? Just download it and then go back to our fancy tools where we fit the moon. Now we're going to slide down 2 of them to the variable tool and upload that same spreadsheet that you just downloaded. Make sure I'm in my download directory. Okay, and here's the bright star, that was the reference. Here's the faint star, that was the RLIRE. This data was taken over the course of 6 days. And you can't tell anything yet, but select the variable star. For me, it was the first one I clicked. It's the fainter, and it subtracts, takes the variable magnitude, subtracts the reference magnitudes, and then you can add in the actual magnitude of the reference star, which is 13.87. It's in your cheat sheet, your sign up sheet. That changed the x-axis, so now all of this is calibrated with respect to that star. And you can see it's varying, but the pattern's not obvious. Everyone here? Go to the periodogram. Students, they don't really need to understand periodograms. It doesn't really matter, but it'll be the faint one. So if I go to none, the faint one, blue, whatever the name here is for you, for me, it's source 10. For you, it's probably source 0 or something like that. You select it, but either way, it's going to work out. You go to periodogram. This is like a Fourier transform. It's a Lomskargel, which is a Fourier transform if the data is not evenly distributed on the x-axis. The students don't need to understand it. They just need to find the highest peak. It's around 0.331, 332. And if you're doing a Cepheid, you have to go to a longer range and check out other scales, but okay, go to period folding. And before you type it in, this is fun. We rebuilt this to help teach what period folding is. You can turn off the 2 periods, just use the scroll bar, and pedagogically, you can see what period folding is. As I decrease the period, it takes it, slides it to the other side. This is a long wait, so maybe type in 0.4, so we don't have to go so far. And I'll bring 2 periods back, and I'll keep scrolling down. That periodogram was a great hint. We know around 0.33, something magical will occur. Oh, there it is. And they can fiddle a little bit. Nothing's ever perfect. These stars probably had a hot pixel in them or a cosmic ray hit, but you got it here. It's already been calibrated, so they take the average. Our libraries have an absolute magnitude of 0.75. They just got the apparent magnitude, and they, math, and they calculate the distance. I'll just pause for a second, make sure everyone's there. Question? You are using, what browser is he using that doesn't have the arrows? What browser are you using? Safari? Firefox. Firefox doesn't have the arrows. Safari should. It's a what? Some interfaces don't have the little arrows, in which case just type in the number and you can tweak the number until you're happy with the alignment. Some browsers don't support the scroll wheel arrows, unfortunately. We are rebuilding all of these tools this summer, and so there may be some additional capabilities. And the last thing, I know I'm in the last 5 minutes, but I'll just show you where this goes next. Nothing you need to do. It only takes a moment. I'm going to go down to the scatter tool in the next lab. In this lab, they learned how to use standard candles. In the next lab, they do the Great Debate of 1920. And so I have data. What we do is we give them a bunch of our libraries to 50, 30 globular clusters. We don't make them do all 150. And they go through an exercise where we gave them the clusters, we gave them the galactic longitudes and latitudes. This little tool makes a top-down map. So I'm pasting in the longitudes and latitudes, and they calculate. We say, here is in our library in each of these, here are the apparent magnitudes. They don't have to go through that same exercise 30 times. We give them the average apparent magnitude. They know the average absolute magnitude of all our libraries are the same. They calculate the distances. We teach them how to do a little bit of Excel logic at the same time, paste those distances in, and then this is a very simple modeling tool. They eyeball the center of the distribution. They eyeball the size. They learn, yes, we're not at the center of the galaxy. They get a size for the galaxy, and later in this lab, they take pictures of what then were called spiral nebulae. We know them to be galaxies now, but there is a big debate. Are they little things and we're the central thing in the universe or not? And we give them Cepheids in those, and they calculate distances, they measure sizes, and they come up, oh, these spiral nebulae are so-and-so light years across, and the Milky Way was so-and-so light years across, and they realized the Milky Way is not unique. So again, our place in space, they're learning the fundamental lessons through observations they're collecting themselves and smart little tools that we've built to make it easy for them. And I think it takes me to the end. I'll just put up the links. There's another page here. If you want additional information, we'd love for you to get involved in Skynet. Again, there's still some money through the NSF grant to help you learn the curriculum, implement it. And, you know, we're already eyeing the next set of grants. We're hoping to double our current user base to set up the next set of grants. We're shooting for a lot of money. And that money also goes to the participating educators who help us make this happen. I'll stop there. Thank you very much. Questions? Just email me. Every fall we have training sessions, and some are really bold and they say, I'm teaching it and training at the same time. You can do that, and we'll be as supportive as possible. But the best thing, we do training sessions every fall. So contact me beforehand, get involved. It's usually on a Friday, 1 hour, and we record them in case you start off season or can't make them. And we help you through the first year, and you master it and you get good. And then you can join the MWU group, which is even more exciting. Yeah. And it's a great community. As I said, we're in 24 institutions. These educators love it. And I can't get rid of them. We meet multiple times a week, designing new curricula, new ideas, exchanging ideas. Often they're the only astronomer at their institution, so this is their community. It's welcoming, non-judgmental, and just fun. And so please join us. Anything else? Okay, I just want to mention we got 2 more workshops. I've mentioned Darrow a couple times. You got to see this HR diagram tool that we've developed. It transcends robotic telescopes. You can use it independent of them, but you can use them with them. And it bridges what students see in textbooks and what we see in papers. And I think it's going to be revolutionary. So please come to that workshop. And tomorrow, Matt Fleenor and I will be taking you through a more advanced MW activity where we'll make a gorgeous picture of the Orion Nebula, not just optical, not just narrowband, but mid-infrared as well. We'll do Stromgren sphere calculations and density measurements, and we'll maybe even check in the radio to see if there's some emission, some brimstrong emission. It'll be a lot of fun. So I hope to see you there as well. Thanks, everyone.
Thank you. Have a good one.
Thank you. Thank you. I forget you're all there, so but I hope it worked out for you.
Worked out well. Thank you.
Good. Yeah. I said, thank you very much. Looked at my watch and boom, 12. Got it to the second. Yeah, I got it to the second.
WCS, plate solved,
Yeah.
dark,
Yeah,
flat.
we do our dark bias flat
You just have
automatic.
a calibration pipeline
Yeah.
and everything's run through.
Telescope maintenance and taking off the camera, and we have to rebuild flats. It can take a couple weeks to get a set of flats depending on how many filters are on the wheel. It can be a little annoying, but that's a small exception. And we have so many telescopes to use a different one. But all the basic reductions are done for them. WCS is put on if you can. Afterglow has a WCS tool that's a little bit better. So if you didn't get WCS, you can try there. Of course, the planetary stuff seldom does that, but the rest is good.
And, yeah, the other question I had, so the sort of funding that you were talking about.
Yeah.
That's, an educator or university wants to get enrolled, and then that pays for like the credits to use.
No, it goes straight to the instructor.
Okay.
So it's independent of your university, it's a consulting fee. For the students, there are 2-3 ways of doing it. If you have a really proactive school, they'll pay. Most people don't. So we've also set it up as a textbook through Cengage Learning, WebAssign, which is a part of Cengage Learning, and it's $65. They keep some, and some goes to pay for the telescope time. So you're distributing it. I know there's a big movement for free textbooks, and this runs contrary to that, but this gains them access to a global telescope network that costs $400,000 a year. So
you have your student.
Yeah.
Require the class to buy the textbook.
Yep. For the regular textbook, I say go to Amazon, go one edition back. And instead of spending $120, they're spending $8.
Okay.
They're
And they
putting
still
the-
get the code.
Yeah. So the regular textbook, you can go free on that
Yeah.
or cheap on that, and they put the money in this, gain some access to really cutting edge modern technology.
And that code then gets each student access to a certain
Yep.
number of credits to do.
Yep. And it gives them with OPIS, there's a lab.
Yeah.
And it's not like formal lab write-ups. It's giving you background. It says, okay, do this, put the answer there. It auto grades a lot of it as well. So if you're teaching 100, it's a lifesaver.
That's awesome.
Yeah, and we keep upgrading them, and the videos are super popular. During the pandemic, we did experiments where no one taught the labs. They just used the videos, and it worked pretty much the same.
Yeah, I mean, we have exactly as you described at the beginning out there, small scopes measure a double star situation
Exactly.
for the observational astronomy class with undergrads. And it's just, it would be so nice.
Yeah. One thing we learned, we did this, and we're like, why are we doing this at night?
Yeah.
We started switching the day, and students greatly prefer daytime labs.
Yeah.
Enrollments doubled just like that.
Yeah. Yeah, no, that is a big, I think.
And the radio, once you get into MW, a little bit in OPIS, but MW,
Awesome. This is very exciting. Thank you.
and I'm glad you're excited. Yeah, email me. I hope to hear from you.
Yeah. Also, sorry, I don't have my name tag. I forgot it in my Airbnb, but I'm in
I
my
I
podcast.
noticed from the
From
the slow result.
Yeah. Yeah. But thank you.
My pleasure. Thanks for coming.